Hi everybody, today we're going to look at Venn diagrams and set operations. Now you may have seen Venn diagrams before, but we're going to go into them in more detail. And they're actually a great way for us to visualize sets. So they're really nice. They're not so the same as graphs, but it's that similar concept where we can sort of see the data. So here we can see the sets and kind of a better picture of them. So we do have to go over some definitions first. And the first one is universal set. So the universal set, and we typically use a capital U here to represent that, is a set that contains all of the elements being considered in a given discussion or problem. So that's like your overarching set or your overarching group. And Venn diagrams are used to show the visual relationship among sets. So again, it just gives us a way that we can visualize sort of what these sets look like. So typically we use a rectangle to represent that universal set. And we'll put like a little U in the corner just to show that this is the universal set. Some applications you may not always see that. So for instance, we tend to use Venn diagrams a lot with things like probability and statistics. So they may not always label it the same way, but it's that same concept of that rectangle being your overarching group or your overarching set. And then we also have subsets within the universal set, and we typically use circles there. So for instance, I'm going to just call this subset A. And then you can see that we have a clear subset of the universal set. So it's not the entire thing, right? It's part of it. So here, A is a subset of the universal set. Now, in all this space here that is outside of A, but still in the universal set, these would be all the elements that are in the universal set, but not in the set A. So your universal set is the entire rectangle. It includes A as well, so it's everything. A is a specific subset we're talking about, but then all this other stuff out here, so that's not in A, is still in the universal set. It's just that it's not in set A. So you do have all that idea as well of kind of this not A piece in the universal set. All right, so what we can do is look at some examples now. Let's just move this down. All right, and I have a couple pictures from the book here for our sets. And we're going to find the universal set, set A, and then the set of elements in U that are not in A. So this kind of shaded in set I was talking about earlier for each of these examples. So I'm just going to call this example 1 and example 2. So for example 1, the universal set is everything in the rectangle. So it's going to be the square and the triangle, and also the $sign, the M, and the 5. So your universal set is everything, all the rectangle. A is just what's in the circle. So it's a subset of U. It's not everything. It's just that one little part. So it's the square and the rectangle. Now the last set is the set of elements that are in U but are not in A. And you can see this in a few different ways. You can either look at the actual roster notation for the sets, and we can see that the elements that are in U that are not in A would be these 3 right here, right? You see the $sign, you see the M, and you see the 5. And you can also see them here. So see how they're in the rectangle, but they're not in the circle, right? So they're part of the universal set, but they're not part of A. We typically tend to write those elements in the corner, although I suppose you don't have to. Okay, so these are elements in U, but not in A. And we can do the same thing for this example here. So our universal set in this case would be all numbers in the rectangle. So I have a 1, 5, a 6, 7, 9. So everything. For A, it's just the elements in the circle, so in that subset, 1, 5, and 6. And then for the last piece, what are the elements that are in U but that are not in A? It would be the 7 and the 9 here, right? So these are outside of A, but they're still part of the problem. So again, just a little bit about reading those Venn diagrams. So let's do a little bit more here with sets. So now we're going to represent two sets in a Venn diagram. So not just A, but A and B. So you have two different subsets. And we're going to do this with a sort of real world application. So we're going to say that we're determining whether there's sufficient support on campus to have a blood drive. Okay, so maybe you're part of an organization, you're trying to organize a blood drive. It's a lot of work to do that, right? You have to have a lot of people come onto campus and you want to make sure people are going to participate. So you take a survey of students to see how they feel about it. And you ask two questions. So the first question you ask is, would you actually be willing to donate blood? And you want to do something nice for all the donors. So the other thing you're going to have is a free breakfast. So if you're not willing to donate, or maybe if you are you also willing to help serve free breakfast to the blood donors? So those are the two main questions we're asking here. Now let's let set A be the set of students who are donating the blood, okay? And then I'm going to just use two different colors. Let's set B be the students who are going to help serve breakfast. And I'm just going to use purple and red to kind of help show those two. Well, basically one of four things that could happen, right? So either no students are willing to donate blood who are also willing to serve breakfast, and vice versa. So you have some students who say, yep, I'll donate blood. You have some students who say, yep, I'll serve breakfast. But those two groups are totally separate. There's nobody who is willing to do both. So this is an example of disjoint sets. And we'll see a picture of that in a second. The other thing that can happen is that all students who donate blood are also willing to serve breakfast. So everybody who's donating blood is also going to serve breakfast. So you have this proper subset where one is a subset of the other. And theoretically, you would assume that more people are going to also volunteer to serve breakfast than just the people who donate blood. So it would be a proper subset. It could be that the same students who are willing to donate blood are willing to serve breakfast. So the exact same students who are donating are the exact same students who are serving breakfast. So they're exactly the same, so you have equal sets. Or what more likely is going to happen than not is some of the students are going to donate blood, and some will also be willing to serve breakfast. So it won't be everybody, but you'll have some who are willing to do both, but not everybody. So these are sets with some common elements. All right, now let's look at what these pictures look like. So in the first case, you have disjoint sets. So they're two sets that have absolutely nothing in common. So what happens with your Venn diagram is you have your universal set here. And then what you're going to see is that you have set A and you have set B. And those sets are not going to intersect or overlap at all. Okay, so they're totally disjoint, like they're two totally separate things. They have nothing in common. Now, in the second example, and the 1, 2, 3, 4 here relate to the 1, 2, 3, 4 above with the student examples. So the second example is that set A is a proper subset of B. So for instance, what the picture would look like here is you'd have your set A, and it's contained totally in your set B. So this is what it looks like when one of them is a proper subset of the other. So everybody who's donating blood is also going to serve breakfast. So you have a proper subset here. A is contained in B. And that's what the Venn diagram looks like. Now, if you have sets that are equal, what we typically do then is we would draw one circle and we would write something like A equals B to show that those two sets are equal. So we're not drawing two different circles. We're just kind of drawing one circle and saying that this represents both sets because they're exactly the same. Every element is the same. There's no even different, right? Everything is exactly the same. And then the last one, which is probably the most common and what we're used to, is when you have some overlap. And so here's our universal set. Here's our set A. Here's our set B. And then what's happening is you have this overlap or intersection in the middle. And these are your elements in both sets, right? So they're in both sets A or B. So for instance, in this case, these are students who give blood and also serve breakfast, right? They're willing to do both of them. So that's your overlapping area. Now, this group here, so A were those donating blood. So these are the group that donate blood, but no breakfast, so they won't serve breakfast. And then this group here are the ones who will serve breakfast, but they will not donate blood. Okay, so just that group in the middle are the ones who are in both categories. So those are the students who are willing to donate and also help serve breakfast. And then again, those who are not overlapping are outside that. Now, beyond your A and your B, anything in the outside universal set would be students who are totally not interested at all, right? So those would be students who are not donating blood and they're not going to help serve breakfast. So they're not interested in the blood drive, kind of lying outside here in the outer regions.